rather than ferromagnetic. So first off, ferromagnetic, once I've done this, it's permanent. It's locked in, unless I do something violent to it. But we can also have effects that are transient, and they're only persistent while the magnetic field on the outside is there. So depending on the atoms in question and how many electrons they have and whether they align or anti-align, lots of things, we can either have examples where the external magnetic field is amplified in the material itself. This is called paramagnetism. Keep in mind a little bit the related behavior we had with capacitors with dielectrics. There's some similarity there, but more complexity. So we can either enhance the external magnetic field, in which case the material is called paramagnetic, or we can diminish it somewhat, again, dependent on the atom molecule makeup, in which case it's called diamagnetic. And in both cases, they're transient behaviors. So, quick, fun couple of things. This is going to be a hard-to-see example of paramagnetism. Okay, what am I about to do? A lot of build-up to this, but it's barely visible, sadly. Permanent magnet has a reasonably strong magnetic field between its poles here. Copper cone surrounded by air. So I'm going to fill this thing with something cold, liquid nitrogen. And as I do so, it's cooling the copper cone on which it's being poured. And eventually, it will be cold enough to cause air on the outside of the cone to condense. So, air is made up primarily of nitrogen and oxygen. This is liquid nitrogen. It has a liquid gas interface temperature of about 78 Kelvin. Oxygen, which is the second most dominant material in air, has a boiling point of about 88 Kelvin. So it boils at about a temperature about 10 Kelvin higher than liquid nitrogen. All of this to say that what is happening now, and you can come and look at this after the end of class, is that oxygen is condensing on the exterior surface of this. It's becoming a liquid. And as it does, it's dropping down here. So in fact, though most of you can't see it because it's clouded by fog, there's liquid oxygen dropping off the bottom. And if you're close to this, you can actually see that the liquid oxygen is being suspended between the poles of the magnet. So this is now filled with liquid oxygen, which is a paramagnet, and it's suspended there, caught between the poles of the dipole. Okay? Just to show you it's really true, I'm going to quickly pull this out of the way and hopefully not freeze my fingers off in the process. And what you'll hopefully see as I remove it is between the poles you'll see this blob of liquid oxygen. Okay? So there it is. You can't see much of it, but it's right there, and it's already boiled away. So that's an example of a paramagnetic material where oxygen in the presence of an external B field is paramagnetic. Its orbital angular momenta tend to reinforce the magnetic field inside the liquefied oxygen. And if you think hard about that, you will see that it has an attractive resulting force with the outside external B field. So I can't show you, sadly, the demonstration by contrast of diamagnetic materials. So I'm going to show you a fun 2-minute video segment instead. So this has to do with the fact that water is a common diamagnetic material. And so the preferred orientation is a little bit different, and it tends to end up with a repulsive force with respect to the outside external magnetic field. So there's a fun way of showing this, which I'm going to show you on this short video segment. And just so you're not alarmed, I will let you know ahead of time that no animals were harmed in the making of this video. Okay, so let's see if this works.
I want to show this is the magnet.
Okay, so what you see there is a very large electromagnet with an aperture, a hole in it. We're going to energize it. And then in the region in the middle, where there's a very strong magnetic field, represent a frog. So this is because the frog contains a lot of water, and it's diamagnetic. So there's a repulsive force between the water molecules in the frog and the external magnetic field. And all sorts of other creatures as well, okay? I don't know what that is.
Or a lot of water.
There is no problem with putting a mount to force a mount by this magnetic levitation to fly in the air. So technically, we can do it with you, without.
Good. Put your body where your mouth is, man. I want to see him float.
No, a lot of you are very enterprising. You love working on interesting scientific projects. You're all making racing cars and all this sort of stuff. Just something to think about, okay? If you want to try and levitate a human, you have an idea now of how to do it. All right, so sadly again, we have no time to talk about materials, magnetism, but you can get a sense that there's a lot of interesting
Water so
phenomena.
float.
All right, questions on magnetic dipole
I'd
moments?
be concerned as a frog.
Okay, so we're going to turn our attention to a new topic which has to do with non-steady state phenomena. This is going to occupy us for the remainder of the semester. So those of you who are here for the introductory comments know that we're starting to talk about changing time-dependent systems. And the first thing we're going to introduce is a phenomenon called induction. So again, I'm going to show you a couple of interesting demonstrations. So let me just reconfigure this. This.
And then I'd high five
All right.
you. Which,
Okay. So let me have you focus on things over here again for a moment. All right. The stuff of interest is this. It's a solenoid. Okay. You're starting to see a solenoid, very much like the one we described briefly in Tuesday's class. It's a multi-loop helical coil. In this case, it's about 6 inches long. It's got an inner aperture of about 1 inch. It's hollow. So it's connected at one end and the other to two pieces of wire. And those two pieces of wire are projected up here on a galvanometer. Okay? So you know pretty much all about all of these components now. And particularly, you know that this galvanometer will deflect if there's a current in this circuit. Is it a circuit to begin with? I've got a wire, a galvanometer. This is connected to this via something conducting, goes over here. And it runs all the way through this loop. So yes, it's a circuit. Right now there's no current. Why would there be? It's not connected to anything. But I'm going to take my permanent magnet and I'm going to bring it close to this. And as I do so, I want you to watch what happens to the needle on the galvanometer. So maybe good enough. Let's go maybe one more. Okay, so on this side you're looking at the screen, so I'm not really in the way. I'm going to take this and bring this permanent magnet and insert it into the interior of this solenoid. What happened?
Induction.
a current for just a little bit while it was moving.
Okay, Jaden, you're going to be tortured now as a result of that. Let's hear more about what happened.
You induced a current by moving the magnet.
Okay, so which direction did the needle deflect?
To the right.
Okay, so right now it's sitting in the middle of that solenoid, but it's at rest rather than the solenoid. I'm going to pull it out. Take a look at the screen.
opposite directions. Now the current's in the opposite direction.
Very
So
good.
it's nudging the other way.
And when it's at rest, either here or here, Eli,
There's a current when there's a change in magnetic field.
a little louder.
There is a current when there's a change in magnetic field.
Okay, starting to see something interesting. There seems to be a current produced when there's a change in magnetic field. That's sort of right. We're going to be a little more precise in a few minutes. Remarkably, we're seeing a current induced in this circuit simply by moving a totally physically, at least in terms of direct contact, disconnected magnet near this loop of wire. Okay, so this is our first example of an inductive phenomenon. This is with a permanent magnet. What I can do as well is, in some sense, something very similar. Here's now another solenoid. It's got a smaller diameter, so it actually fits inside. I can maybe just drop this inside in such a way that it's now nested in the center, but it's not physically touching the outer solenoid. And if I turn on a current through that inner solenoid, the instant I turn it on, there's a deflection. When it's on consistently, there's nothing. When I turn it off, there's a deflection in the opposite direction. Okay? So now we're seeing something that tells us whenever we have something that has magnetic field associated with it, and there's something changing about that magnetic field with respect to, in this case, this solenoid here, we induce a current. Okay, so these are our first examples of inductive phenomena. All right, so I'm going to say a couple of things which if you guys had 5 minutes to play around with and you were a sharp observer doing an experiment, you would deduce fairly quickly. And as with many laws in physics, they simply come about by people taking a bunch of observations and trying to write them in a concise mathematical form. Okay, so that's exactly what we're going to do here. So what we've observed, first off, is that we see a current in our little galvanometer there only when there's relative motion, or when a magnet is turned on or off. Okay? So the latter referring to an electromagnet, of course. You didn't see this, but you could if you did an experiment for a couple of minutes. So let me say faster relative motion. You would see produces a larger current. So whatever this effect is, seems to depend on how quickly the magnetic field is changing in this area of interest. And we also see that there's a change in the direction. Depending on the relative motion. So, simple phenomenon, but it includes a lot of actually interesting, subtle behaviors. So, let me sort of try and consolidate a little bit what we're observing, and it'll very quickly get to us to a useful equation that characterizes this. Just as I'm erasing the chalkboard here, what do I need in a closed-loop circuit in order to have a current flow, as we just observed? What's the underlying phenomenon that drives a current flow in a circuit? Some kind of EMF, yes. So, good. Underlying this is an induced EMF. Okay, induced in the sense that some of the phenomena we just looked at are causing or inducing this EMF to appear. It's not like it just comes from the battery or hook up to things. Okay, so again, if you had a little bit of time to do some experimentation, what you would eventually learn is that the key quantity that actually defines the magnitude of this effect is the magnetic flux. Okay, so quick reminder / aside on magnetic flux. How did we define electric flux a few weeks back? So give me a concise definition of electric flux, and it doesn't have to be through a closed surface. We're not yet talking about Gauss's law, just generically electric flux.
I was going to give that other answer.
That's all right. I mean, most of what I want is there, but there's a little bit more in Gauss's law. But just think of Gauss's law and just tell me what the electric flux part of it is. So forget about the rest of Gauss's law.
The integral of the electric field dot the area.
So that's the electric flux, right? So we defined this maybe a month ago. The integral of electric field, scalar product area element over some surface. Okay, some surface. Doesn't have to be a closed surface. It only becomes a closed surface when we break this Gauss's law. This is the electric flux. We talked a lot about how this is driven by three things here: the magnitude of the electric flux, the area concerned, and the relative orientation of the two. Okay, so a little bit involved. No big surprise. We're now going to define the magnetic flux. That. Okay, so subscript B for magnetic field, subscript E for electric field. So there's the magnetic flux, and it turns out this is the driving quantity that's giving rise to these inductive phenomena. So I'm not going to go through again the derivation or quite what this represents geometrically. At this point, you know it pretty well. In terms of units, SI units, Tesla meters squared. Okay, so here's now our magnetic flux. And again, you could, with some reasonably detailed experimentation, you could kind of determine that this is what drives these phenomena. So it immediately turns out that pulling all of these pieces of evidence together, we can arrive at a concise representation of, whoops, Faraday's lens, that's not good, Faraday's law. Which characterizes all of these behaviors. And here it is. So again, it's super concise, which is nice. It's elegant, but it has quite a richness of phenomena underlying it. So let's take a look at it. Okay. First off, EMF, and it's an induced EMF. So in case we have a circuit, as we do here, it's that induced EMF that's driving current around the closed loop. Okay, that's easy enough on the left-hand side. The right-hand side is a little bit more involved. Okay, so here's the magnetic flux. We just defined it. And what's most critical about this is for the first time we see an explicit time dependence. So d phi, the flux, by dt. So here's our explicit time-dependent behavior. Okay, so if the flux through some region of interest, defined by the area, changes with time, this tells us we induce an EMF. And if there's something that can have charge parity move through it, namely a conductor, then there will be charge moving through it. So changing magnetic flux in a certain area induces an EMF, and if there's a conductor, it will drive a current. And then lastly, this. And this is an interesting and again quite subtle thing. So there's a minus sign. It has to do with the following. It's a little bit hard to describe just in words. We kind of need to look at specific examples. So the minus sign indicates that the EMF is induced such that ST, it opposes the change in flux that induces it. Okay, this is quite a mouthful. Okay, but it's the aspect that's key. We'll see what this means maybe in an example in just a moment. Okay? All right, so let's see if we can explore this minus sign a little bit more. Before doing so, let me just remind you of the ways that the magnetic flux can change in a certain region. First off, the magnetic field itself can explicitly change with time. I'm going to give you a working example of that in just a moment. Secondly, perhaps less commonly, though we can look on Tuesday at a very crucial application where I'm about to say holds, the area through which the magnetic field passes may change. Okay? So this may change, or the relative orientation of these two things may change. If any of these things change, I know I'm going to induce an EMF and again possibly current. All right. So, nice, beautiful, simple way of characterizing all of this. So this oppositional aspect is sort of sufficiently interesting and rich that it actually has a name associated with it as well, which I'm not quite sure if it's warranted, but anyway. This part of it is sometimes known as Lenz's law. It's the negative oppositional aspect that Lenz is attributed with. Okay? So really it's just a single behavior in terms of Faraday. All right, so let's look at this oppositional aspect in a couple of different ways. I guarantee at some point you might get a little bit confused by this, so just pay attention for a couple of moments and read through this stuff on your own time. We've seen a few examples recently where directionality can be a source of confusion, but here's another one. So on the left-hand board, I'm just going to talk through this for a moment. And it's the sense in which we can say something about this oppositional aspect. So, top sketch. A single, let's say, closed circular loop of conductor in yellow. I'm going to take a simple bar magnet. And I am going to imagine taking this loop, conductor, I'm going to bring, let's say, a bar magnet closer and closer to it, maybe even going through the middle. And the way I've drawn it here is with the north pole coming downwards. Okay? All right, so what I want you to think about is if the area of interest is defined by the circumference of this ring, so just think of it as a circular disk, it's the area of interest. Now I'm bringing this closer and closer to it. You know what the magnetic field lines around this magnetic dipole bar magnet look like. So it's kind of the thing that was on the chalkboard at the start of class, so it's the dipole shape with the lines wrapping around. Think about how the magnetic field lines passing through this imagined surface now, how it changes as I bring this closer. Okay, so it's a complicated effect, given the shape of the magnetic field lines around this, but suddenly you know the magnetic field is getting stronger and stronger as I bring this closer. So the question then is, what does Faraday/Lenz law tell us about the induced EMF and therefore the current that's being induced in this coil? And there is a current being induced in this coil. It's not hooked up to anything, we can see it, but there's a current flowing around this as I do this. So what can you tell me about Faraday-Lenz's law in terms of the direction in which the current should flow as I do this to give that oppositional nature of the minus sign, the Lenz's law? It's going to induce an EMF and a current which tends to oppose change in flux. So this is subtle and it's not easy the first time through. So I want you guys to tell me how you think this is going to go. So, you're scratching the back of your head. Okay. Well, let's put you on the spot. Okay. Any ideas about?
I mean, I do know that if you're pulling it in and pulling it out, there's an opposite direction of the current. But in terms of what direction that is, you have to do some right-hand rule.
Okay. Anyone want to help him out? Yeah.
So when we say that when the magnet,
By the way, the answer's on you.
yeah,
Right.
when the magnet is approaching wants to do is to decrease the B
Right.
field. So then it would induce a B field that opposes the increase in B field, which is going
Nice.
down.
Yep.
And then since the induced B field is this, then no, the induced B field is going up.
Yes.
So then the induced current would be going.
Yes. Okay, so I gave you the answer, okay, so then you wouldn't have time to do it justice if I did it on the fly. Good, nice explanation. So right now, let's say I've got this such that I've got a north pole coming down this. As this comes closer, what the induced EMF and the current that it drives will want to do is circulate in such a way that it produces a north pole that is in a sense opposing this approaching north pole. Okay? And in order to do so, as you correctly pointed out, you would have to induce a current that is going around in that sense. Because, here's my curled right-hand rule, I'm following the current in green, and the magnetic field that's produced in the middle is upwards from our curled right-hand rule. And you see, for good measure, I threw on the blue magnetic dipole moment associated with the induced current. Okay? So yes, opposition. It's going to produce a magnetic field based on the circulating current that tries to push away this incoming north pole. Okay, think of it in the opposite sense. If I pull it away, how's it going to respond? Right, it wants to pull it back, right? So I've got a receding north pole in this case. It wants to induce a current which produces an attractive south pole to pull it back. Okay, so this is complex and it's easy to get confused by. So yes, in that sense, it's going to send a current around in the opposite direction. So there are a couple of ways to think about this. And I'm going to encourage you to work this through on your own, because if you don't do it now, I guarantee you'll trip up at some point in the future. So do it now, use textbook notes or whatever, just to make sure you're okay with this and get this oppositional aspect down. Okay. All right, good. So there's the oppositional aspect of lens, but here's the overall Faraday lens law. Okay, so we're going to use this quite a bit for the remainder of today, and certainly Tuesday next week, to look at some of the interesting phenomena associated with it. All right, so let me show you a couple of things now, just to show you some of the fun effects associated with it. All right, so big solenoid. This is probably the biggest solenoid you're going to see in this course this semester. Pull this out. Big solenoid connected to a current supply, a switch. It's not yet turned on, but it will be in a moment. So I'm going to drive a pretty hefty current around this multi-loop solenoid. As I do so, you now know it's going to produce a magnetic field that in the center is axial. And it's going to flare out, as we've seen many times now, as it wraps back around so that we have a continuous magnetic field line. So fine. Here's an example now of a piece of ferromagnet. It's a chunk of iron. I'm going to put it in here. It has the exact same effect as you saw with that one over there. It has the effect of kind of focusing the field lines in. And it protrudes out the top here so that field lines, which in the absence of this would kind of flare around, wrap back around, they're kind of focused in here and they don't flare until they come out the top here. So it's kind of bunching the field lines together. Okay, so now what I'm going to do is take a freestanding conducting coil, piece of copper, put it on here. Now, when I turn this on, it's going to be not a direct current, which is to say a current flowing in one direction, but it's basically current that's coming out of the mains, out of the outlet, which is an alternating current. Okay? We learned a little bit about alternating currents a couple of sessions back. That's naturally what we get out of that turning loop in an external magnetic field, unless we apply a commutator to make it DC. So alternating current. It's going back and forwards, and I'm embarrassed to say every time I do this, I forget what it is. I can't remember if in the US it's 50 hertz or 60 hertz, which the outlet goes back and forth at. Anyway, it's many tens of times a second. So it's changing 50 or 60 times a second in terms of the current direction. 60, thank you. Okay. The reason I get it mixed up is because it's the other number somewhere else. Okay, so the current is changing direction 60 times a second. What does that tell you about the direction of the magnetic field through the center of the solenoid? flipping back and